Good morning and welcome to Minerals, Rocks, and Fossil Talks. It's time for Monday's musings, and we're going to talk about macrocrystalline quartz versus microcrystalline quartz. I see so many people in rock hounding groups and other places arguing over the varieties of quartz, and it gets a little frustrating because people get really defensive when you tell them that your agate really is just quartz with a microcrystalline structure, and it just happens to have these fun patterns in it due to impurities and due to the way that it was formed and all this, but it's really the second most abundant thing out there in the crust. And then they're like, how dare you, it's rare. Anyway, I'm not saying it's not pretty, guys. It's still a pretty piece of quartz, but still just quartz. Anyway, so I think it's important to address this and just show people that quartz is amazing because it has so many ways it can look and be. So let's start with the basics here. So at the heart of it all quartz is simply silicon dioxide. It is one silicon with two oxygens. Now, if you'll recall from a previous video, I did say that it had a perfect three-dimensional tetrahedral shape, and that is because the oxygens share electrons and want to be close to each other, and so they connect and make the tetrahedron. But at the very, very base of it all, silicon dioxide is the chemical formula. So whether it's amethyst or chert, agate or chalcedony or rose quartz or whatever, they all have this chemical formula. So what makes them different? It really is based on how they are formed, how they're created. Macrocrystalline quartz grows by adding molecules to the surface layer by layer. It essentially grows in three different environments. So the first is silica-rich molten rock during cooling and solidification. So for example, this piece of granite here, the formation of quartz is caused by positively and negatively charged ions floating around in the molten rock soup. In fact, these silicate ions cause the magma to become more viscous. So the more SiO4 minus you have in your magma, the more viscous it gets. Now, SiO4 minus usually forms long chains in the magma. So when magmas cool rapidly, like at the point of an eruption, the chains don't have time to break and new bonds to form, so silica-rich magmas often form volcanic glass, like this obsidian, or pumice. So they're still in that chain pattern, which is why you don't get, your typical quartz shape. Now, when magmas cool slowly under the surface, like in granite or this pegmatite, crystals of different minerals will melt in order of the chemical composition of that magma. So with granite, micas will form first, the feldspars will then follow, and then quartz is the last. And because it's last, it doesn't make that perfect quartz crystal shape because it's filling in all the holes and spaces that are in the rock as it solidifies. So it's just kind of expanding to fill the space that's available. The final way to form macrocrystalline quartz is through hot water solutions of silica-rich water under various conditions, usually hydrothermal, and not this kind of hydrothermal. I just really thought this picture was pretty. It was from a trip I took to Yellowstone. Anyway, when I say hydrothermal, I mean under the ground where the water is between 100 and 450 degrees Celsius, and it's at high pressures. So it does have to be underground. there's no free SiO2 molecules in the solution. Instead, quartz crystals grow by the addition of dissolved orthosilicic acid, so that's H2SiO4. And then I'll show you a diagram of kind of what that looks like. So basically, as the orthosilicic acid is broken apart, the SiO4 starts connecting to each other. And so you start seeing these shapes that start making crystals. So that's neat. And then it ends up filling in those hydrothermal veins that you'll see in rock. And just a little thing to add to the magma quartz formation. They'll often have an onion-like internal structure because the layers are being added on top of each other, which reflects a gradual change in the residual liquid parts of the solidifying magma. Because there is a little bit of water in magma, and that water will have dissolved ions in it, and yeah, so there you go. Okay, now on to our microcrystalline, which are usually called chert and or chalcedony, and a bazillion other names of different varieties: jasper, flint, agate, all that. So chert can form under two processes: biochemical and replacement through solution in water. So first is biochemical chert. Biochemical chert is formed when siliceous skeletons of marine plankton are dissolved during diagenesis, with silica precipitating out from the resulting solution. You will usually find siliceous chert in limestone. A good place near where I live is Provo Canyon. You go up Provo Canyon, there's big black hunks of chert in the limestone where these siliceous marine planktons were diagenetically dissolved and precipitated out as chert. It looks really cool. The other way chert can form is through replacement, when other material is replaced by silica, usually by water, such as petrified wood, dinosaur bones. It can fill just about any type of fossil. So replacement fossilization is usually by chert. Now, chalcedony also forms by precipitation of dissolved silica in water, but it is usually formed from watery silica gels, which give it the botryoidal look it is well known for. So that's what you're seeing here, that sort of bubbly look. It is often deposited in cavities and fractures in spaces that are too small to form proper quartz crystals, which is why it comes out microcrystalline. And sometimes it's by the release of silica from weathering of other rocks, usually volcanic rocks. And technically, chert and chalcedony have different forms where they, at microcrystalline, like you'd have to look under a microscope. Well, they'll talk about like fibrous versus grainy. In reality, they're both kind of grainy. So they kind of just lumped them all back together as varieties, but they do form under different circumstances. But as you can see, it's really just about how they form and not about what they're made out of. In reality, they're all quartz, whether it's microcrystalline in structure or macrocrystalline in structure. It's all got the same hardness, it's all got the same fracture, they've all got the same properties for the most part. Some things change, but it's all quartz, and it's all cool. And it's okay if your favorite rock is really common. So I hope you guys learned a bit about quartz today, and I will fossilize you later.